Welcome back, my dudes. This is 70 climbing stairs. So this one, I'm not gonna lie, it's kind of a banger, okay? This one's kind of tough. If you're not used to DP, first time solving this problem, by the way. If you're not used to DP, it's gonna be a little bit tough. But I'm gonna explain it, and then I'm gonna draw it out, and hopefully it'll make sense. But you are climbing a staircase. It takes n steps to reach the top. Each time you can either climb 1 or 2 steps. So no matter what number we have to get to, we can only take we have a binary amount of options, right? And so you should start getting some cues here. We have a binary amount of options. We can either take 1 or 2 steps. So in how many distinct ways can you climb to the top? So if we take a look, we have n here. N equals 2. So and the output is 2. So there are 2 ways to climb to the top. If you start at the first step, which is 0, so on the floor basically, you can take 1 step and then another step, and you get to the second step. But if you were to start back on the floor, you could just take 2 steps to get to 2. So you can only take 1 or 2 steps. Now we have another example here, n equals 3. So we want to get to the third step, and so they're going to show us how many different ways we can get to the top. So you can take 1 step, 1 step, 1 step, or you can take 1 step and then 2 steps. And what's cool and is important to note here, they kind of show with this example, is that order doesn't matter, or order matters. So if you take 1 step and then 2 steps, that's different than taking 2 steps then 1 step, right? So they just want how many different ways you can get to the top. They don't really care if you kind of take the same delineation of steps, as long as you can get to the top and you haven't used that method before, right? So there's a few different ways to think about this problem. So oftentimes when you have problems like these, your intuition should be, can you solve this solution, or can you create an algorithm, or can you create an answer that is defined in terms of itself? So when the problem presents itself this way, you can kind of see that in a way, it's kind of saying, I can be solved in terms of myself. And when you can do that, you can also employ dynamic programming. And I'm going to show you what I mean here in a little bit. But if we switch to this, boom. So the problem said, right, let me just pick any random color. Oh, my thing is... So if we take a look at this, so we're just going to work through this a little bit, right? So they gave us a sample, right? So n equals 3, right? And the answer equals 3. So there are three ways to get to the third step, right? So you can kind of work through this, right? So let's just say we started at 3, and you know how they gave us a binary set of options, right? So this should kind of signal to you, oh, there's going to be some, let me move this over a little bit. There's going to be some binary tree action. So I'm going to make this a little bit smaller so we have space. But, so we're at 3, right? And the thing that's important to note is that this problem is the same whether you look at it from the top or the bottom, right? What do I mean by that? So if you change the way the problem is worded, right? You're saying you're climbing a staircase. It takes n steps to reach the top. How many ways can you climb to the top? Well, it's the same thing as saying you're starting at the top of the steps. How many different ways can you get to the bottom, right? Essentially, the question is the same. We're just starting from a different end. The answer is going to be the same, though. So from this angle, we're kind of starting from the top. So we're going to start at the third step and say, well, how many steps or how many different ways can we get to the 0th step, which is the step on the floor? And they said we can only take 1 step or 2 steps, right? So let's kind of draw that out. So if we wanted to take 1 step, right, we'll just say this is -1. We took 1 step. Now we're at the second step, right? Okay, well, let's take another step. And we'll put -1 here just to show or kind of hint at what's happening. But we're going 1 step down, right? And then we're not at the bottom yet, right? So we need to take 1 more step. So you get 0. So the thing that's important to note here, once you hit 0, that's good. It means you were able to reach the step using the path that you took, right? So let's kind of work through the other steps, right? So we kind of went straight down as if we kept going down one step, right? But since this is a tree, we can kind of just work out the other remaining steps that we could have taken. So 1 here, we could have taken 2 steps down, or taken 2 steps down from here, right? So let's see what that would have looked like. So it says we can only take 2 possible choices, right? You can either go up 1 step or up 2 steps, or in this case, you can either go down 1 step or down 2 steps, right? So in this case, we're just going to pretend that we went down 2 steps. But wait, you get -1, right? That's lower than we wanted to go. So that means the path we took to get here is not a possible path that we could have taken. It's not a possible path that you can take to reach 0 or the top step, which is 3. So remember, we're going from top down here, but you could do the same thing going bottom up, and I'll show you that in a second. But just to write out the possible answers, so in the example, they gave us these possible step combinations. 1, 1, let me make these ones a little better. 1, or you can either go 1, 2, or you go 2, 1. And you'll see that we're going top down here, but the answer is still going to be the same. And we already saw this here. We can go down 1 step, down 1 step, down 1 step, and we can take this path to get one possible way to get to the bottom. So we already did 1, right? So let's go back up here to 2, because we can only take 2 steps, or 2 different possible. I mean, we can only take 2 different options, either going down 1 step or going down 2 steps, right? So this is why this is modeled as a binary tree. So let's do this one right here. Well, we already took 1 step down on the left-hand side, right? So let's take 2 steps down on the other hand. And we'll get 0 here. Wait, that's kind of dope, right? So the great thing here is that we realize that we can get to the 0th step from 2 if we take 2 steps down. That means a possible path is -1, -2, since we're going since we're going top down here. But as we can see, the answer that they had in the example, they're going bottom up. So they're going up 1 step and then 2 steps. But here we're just going down 1 step and then 2 steps. We still get the same answers, right? We got this one already, and we got this one already. So let's see what remained as the other possible options. Well, we already took these 2 possible options, 2 and 1. So let's go here. So we started at 3, right? We already took 1 step down. We saw how far this takes us. So let's see where this can take us. So this was down 1 step, so we have to take down 2 steps here. Okay, we're at 1. At 1, we can either take 2 options, right? Down 1 step or down 2 steps. And notice how I do this in the very specific order each time. If I start a node, I go from the left. I go as far left as I can, and when I can't go any further, then we go back and we keep going. So we take 1 step down here, and we're like, oh, we got 0. That's kind of dope, and I'm just going to mark all the ones we got 0. That's dope, which means you can go down 2 steps and then down 1 step. 3 possible answers. Well, where does this one lead, right? Well, let's say we go down 2 steps from 1. You get -1, right? So that's not good. So what you see here is that this problem can be defined, the answer to this problem can be defined in terms of itself, right? Because if you look at these nodes, there's a lot of similar nodes. We have 0, 0, 0, -1, 0, 0, 1, 1, right? And you see like a lot of them start to repeat, right? I mean, we have a very small tree here starting at 3 just to make it easy to draw. But there's a lot of repeating nodes here. So if that's the case, well, why, like I said earlier, this is the dynamic programming problem. So if you look at this problem like this, you can solve it like this, but the problem is the time complexity here is going to be 2 to the n, which is very, 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 very slow. And a lot of that is due to the fact that we're going to be recalculating nodes that we already know the answer to, right? Once we know that from 1 there's 1 possible way to get to the bottom step, why do we have to calculate this again over here, right? Because that kind of doesn't make any sense. And you'd see how ridiculous it gets if I were to add 4 up here. So if I were to add 4 up here, then you'd find that 3 is duplicated. You get this entire tree just duplicated under 4 on the other hand side with, you know, repeating values and recalculating values as well. So that's why that's really slow, right? But if we know the value of what the nodes are going to be already, well, why can't we just save them, right? Why can't we just save them? And if we ever run into a node like 1 or 1, we know that the answer is not going to change. If we get to 1 here, we know that there's only 1 possible way to get from the bottom step from the first step is by taking one step down. If you take 2 steps down, then you don't get there, right? The answer doesn't change if you're from here or if you're from here. It's the same answer. So we can just kind of save these answers in whatever your choice is. As long as your lookup is constant time, then you're fine. But you can imagine if you take a look at this, let's just say we were to save it in a memo. And for our sake, this is just going to be a dictionary. And so what we're going to map to is the node. We're going to map the node to steps taken, or steps, let me remove that actually. Steps to reach 0. And if you're going bottom up, this is just steps to reach n, right? And so what does that look like? Well, we have node 1 here, right? So we could have node 1 in our dictionary here, and we could just say, well, we know from once you get to node, if you ever see a node 1, then it takes there's one way to get from 0 from 1, right? So if we ever see a 1, anytime we look at a node, anytime we start a node, we're going to say, hey, have I seen this node before? And if I have, just get me the value we already recalculated. Instead of get me the value we calculated already instead of recalculating it. And if we haven't seen it, well, let's calculate it, right? So how do we calculate a value for a node? Well, the reason I said this problem is defined in terms of itself is because if you take a look at the nodes, I mean, it has a binary structure to it, right? And so what you'll see is that values of nodes are defined in terms of values of other nodes, right? So what do I mean by that? 3, right? We know that the answer, right? If the question is asking for how many steps does it take, how many different ways can we get to step 3 from step 0? We know that the example gave us 3 ways, right? How can we tell that from this graph? I mean, this tree that we made, right? Well, we said, well, 1 means when you see the node 1, you have one possible way to get to 0, right? And when you see 2, there's 2 possible ways to get to 0, right? So you can either go 1, 1 or -2, and we can see that. So here we have 2. Oh no, I mean I said that the wrong way. 2, I think, is the same. Yeah, so 2, that's my bad. So 2, there's only one way to get. Oh, no. Okay, I confused myself. So yeah, from 2, we can see that the way you get, how many different ways you can get to 0 from 2, there's 2 different ways, right? Because if we follow the tree down, I should use different colors. But you can see that we reach 0 at this point by going 1, 1. And we reach 0 this way just by going -2, right? So the way that works is if we look at both trees, we can see that, both paths, we can see that they both end up at 0 somehow. And we can save that, right? And so, like we said earlier, if we haven't seen the value before, then we'll save it. And so the way we can save it is by doing the addition of what both of these, I guess, paths would evaluate to, right? So I'm going to show you what that looks like in code. So let's switch to code. Boom. So the problem said you are climbing a staircase. It takes n steps to reach the top. Each time you can either climb 1 or 2 steps. How many distinct ways can you climb to the top? Well, I'm going to show you bottom up and top down. And so since the example, what we drew was top down, we're going to do that. So what we're going to do is we're going to define first our memo. And this is just going to be a dictionary holding, the index to how many different ways you can get to 0 from that number or index, right? And then we're just going to return climb n and then we're going to pass in memo, right? And then we're just going to define that here. Oops. And then we're just going to pass in a dictionary. Let me see something real quick, actually. Okay, I had to see if you had to declare the types. You don't, because I was going to say, I don't remember. But, so we're in this, so we have, this is our function that's going to be called to call the solution, right? But we're only going to call it once here, and then this function is going to be defined in terms of itself up here. So this is going to be the function, climb is going to be the function that actually does the work, right? So when we were looking at the tree from earlier, we said that once we reach 0, right, that's good, right? That means we got to the end of the function. I mean, we got to where we want to be, right? We were able to find a path that led us to 0. So that's good, right? And so what we want to do there is if n is equal to, actually we're going to pass in one more thing. So I is going to be where we start, and n is going to be our end value. Or no, we're going top down. So we're just going to pass in n. See, it gets confusing. Boom. And we pass in n here. So because we're going towards 0, we don't actually have to know where we start, because we're going to get passed in where we start. And so if n equals 0, so if we get to a point where n is equal to 0, that means it's good, right? Return 1. And so return 1 is going to make more sense because we're going to summate the values as we're going up, and so we're going to be able to add to those answers. And the second thing, right, we're going to need to do is we're going to need another case, right? Because we're going down, since we're going top down, we're going down 1 step, we're going down 2 steps, right? But if we're at 1 and we go down 1 step, we hit this case, right? Which is dope. It means we found a path. But if we go down 2 steps from 1, we hit -1, right? And we don't want to be at -1. That's not a valid path. So if n is less than 0, we're just going to return 0, right? And when we summate that going upwards, it basically means that if we ever reach a path that doesn't get us to where we want to be, which is at the bottom step or the top step, then what we're going to do is we're just going to add 0, which is pretty much going to mean don't change our answer, pretty much. And the other thing we're going to want to do is we're going to say if n in memo, right, then just return memo sub n, right? Because we don't want to, if we already saved the value, we know how many steps we can get to from this node, then we don't want to recalculate it, right? Like we said earlier. If we have to recalculate every node after we've seen it, then we're going to end up with 2 to the n runtime, which is unbelievably slow. And then this is kind of the magic sauce here, the magic sauce. So memo sub n is going to be equal to, so this is the part where we do kind of the binary portion, right? And just to make this make a little bit more sense, I'm going to write the code first, and then we'll take a look at the picture we drew. But we're going to have to call the climb function again, but this time we're going to do n minus 1. We're going to pass in memo, just because we're kind of carrying this thing along with us. We're kind of carrying this dictionary along with us to see if we haven't seen this value before. Climb n minus 1 plus climb of n minus 2 of memo. And then we have to save the value, right? We said if we get past all these cases, okay, we haven't seen it before. It's not 0, so it's not a valid path. And it's not less than 0, so it's not an invalid path yet. Then we're just going to calculate it, right? Because we don't know what the answer is yet. The thing is, one or both of these will get to their bottom, and they'll eventually equate to one of these. That value, those two values will get summed together and then saved to this index. And then we're going to return memo sub n. And if we, climb is not defined, I probably have to do self.climb. And I probably have to do self.climb here. And that's going to get us the answer, right? So there are two confusing things we kind of just did, right? We said memo sub n, what are we doing there, right? So I'm going to go back to this screen. We said memo sub n equals the value of these two nodes, right? And so what we're going to do is going to kind of redraw what happened, but this time we're going to do it in the form of memo, right? So you have 3 cases basically. If seen, return seen value. If n equal 0, return 1. If n less than 0, which means we have a negative value, which means we went further than we had to, we're going to return 0. And the smoothing is kind of messing with it here. And then else, which is not really an else, but we're just going to say memo sub n equals climb n minus 1, and I'm going to exclude memo here because we already know that we pass in memo in the function. We're just going to save some time here. Minus 2, right? And then return. Oh, that's awful. Memo sub. So we're going to calculate the value and then return it, right? So then what I'm going to do here is we're going to visualize memo down here. And so we're going to do it from top down, right? So let's just do, we did 3 earlier, right? So we're just going to do 3 again. And our memo right now, it's a dictionary, right? It's empty, right? I'm just going to move the 3 over a little bit so it's easier to see and make it smaller. And so what we're going to do is we're just going to follow this line by line. It's going to make a lot more sense. So what's going to happen is, okay, we called climb, right? Now climb is going to go into this function. It's going to say, hey, if seen. Actually I said seen in memo, but this is basic. Seen is basically memo. That's my bad. But so we're going to return the memo value. So if in memo, if n is in memo, then we're going to return memo val, right? So let's just work through this. It's only going to be a couple of calls. It's going to be much shorter now. You can see that we're using the memo. And so what's going to happen is we start at 3, right? We called climb. We passed in the value we got from the LeetCode, right? We passed in n, right? So we're going to go in here. If n is in memo, where our memo is empty, right? So we're clearly not going to do this portion. Well, does n equal 0? Well, n is equal to 3. So that's not true. Is n less than 0? Well, n is not less than 0. So can't do that. Well, then we're just going to calculate it. Memo sub n. So we're just going to add n here. N is going to be equal to 3, and then I'm going to do it like this. I'm going to put a blank line plus blank line. And this is going to make a lot of sense because we're doing climb of n minus 1 plus climb of n minus 2, right? So we don't know what the value is, so we have to go get the value, right? So now it's going to call climb of n minus 1 now. Climb of n minus 1, right? And I'm going to do minus 1 here. Climb of n minus 1 is 2, right? So let's just go through and follow like we said. Is 2 in the memo? It's not. Is 2 equal to 0? It's not. Is 2 less than 0? It's not. So we're just going to calculate 2. We're going to say 2 is going to be equal to climb of n minus 1, which is 2, plus climb of n minus 2. Well, okay, so now we're in for a round with 2. I'm going to say, okay, minus 1. And now you're going to see why I went straight down the left side the first time. Is because this is kind of the way recursion works, right? We're always going to call the first function, and then the first function is going to call the first function again. And by first, I mean the first climb instead of the second climb. So now we're at 1, right? Okay. If is 1 in memo? It's not. Is n equal to 0? It's not. Is n less than 0? It's not. Okay, then we're just going to calculate 1. 1 is going to be equal to blank plus blank. Climb of n minus 1 plus climb of n minus 2, right? Okay, so let's do 1 now. Let's go a little bit deeper. Now we're at 0, right? And this is where things are going to start to change a little bit. So let's take a look. Is n in memo? 0 is not in the memo, so I don't know what they're talking about, right? Is n equal to 0? It is. So return 1, right? And this is the first time where you're going to get propagation up through the tree again, right? So we said we're going to return 1. So okay, we're going to return 1 here, right? And now we're no longer in this bottom part. We're in 1 now, because we said return 1. We're not returning 2 functions this time, so we're not going any deeper. We're just going to return 1. And we're going to end up right here. 1 said climb of 1. It said memo sub 1 is equal to climb of n minus 1 plus climb of n minus 2. So you have the first part right here. From 1, there's one way we know right now to get to 0. What we do know is that from 1, there's only one way. If you do minus 2, you get negative 1. There's no way, and you're going to see that here. Plus climb of n minus 2. So let's do minus 2 here. Oh no, you got negative 1, right? So let's call this climb function for negative 1, right? Is n in memo? Negative 1 isn't in the memo. Is n, which is negative 1, equal to 0? No. Is negative 1 less than 0? It is. Return 0. So we're going to return 0. So now we know that from 1, there is only one possible way to get to the bottom step, right? And that is going to mean that 1 is equal to 1. This is our first completed part in the memo, right? But now we're going to go back up right now to 2, because we went down 1 step from 2, right? So how else can we do that? So now that we have 1 completed, right, we can shoot back up to 2. Remember we said memo sub n, which is 2, is equal to climb of n minus 1, right? But now that 1's completed, we're going to get 1 here, right? And you can see that because we already did minus 1 here. We know what it evaluates to, right? So when you're working through the tree, you want to go down as far as you can. Then you're going to go the left branch, go up 1, right branch, go up 1, right branch, go up 1, right branch, go up 1. And you just want to go as far as you can before you start going the other way. So what is climb of n minus 2, right? We're going to do, it's kind of hard to draw, not going to lie, minus 2, right? And then here, what we get, remember we said, we noticed before, right, that there were 2 ways to get from 0 from 2, and we can see that, minus 1, and minus 2, right? So that's pretty dope, right? So let's run this for 0. Is n equal to 0? It is. Return 1. So now we know that from 2, 1 plus 1 is equal to 2. Right? And 2 is completed. Remember we said memo sub n is equal to climb of n minus 1 plus climb of n minus 2. That's what's happening here. This is climb of n minus 1 and this is climb of n minus 2. And this kept going. Right? And now you're going to see this speed up really fast, but there's only one node to save time. But now we're back at 3, right? Remember we said 3 was equal to memo sub n is equal to climb of n minus 1 plus climb of n minus 2. Well, what's climb of n minus 2? Oh, and also, what you see here is that this also comes back up, just like we said it was happening. We said 3 was equal to climb of n minus 1 plus climb of n minus 2. Well, we did climb of n minus 1 and evaluated the plus 2. In this one, we'll only see that the memo saves us 1 calculation, but when you go much higher, you draw a larger tree, you'll see that it starts to save you a lot of calculations. And we'll see that here. So let's do climb of n minus 2. What you get is 1, right? And now this is the first time you see if n is in memo. Well, let's check. Is 1 in the memo? It is. There's only one way to get to the 0th step from 1. So 2 will just return that value. Remember we say return memo value if it's in the memo. So 3, so we know that for 3, there's 3 different ways to get to the 0th step, right? And we're going to do this one more time just to show you. This is top down, right? So we're starting at 3 and want to go all the way to the 0th step. So now we're going to do this in reverse. We're going to do this from bottom up, right? And what you notice is that not much really changes. There's a few things that we're going to change in the algorithm, and you'll see it here. So if we're doing bottom up, right, it means we're going to start at 0. And we're going to change the algorithm here in code. If n is in memo, return memo value is going to be the same, right? Why would that change? But you're going to realize that these 2 cases are going to change. So when do we stop, right? Before we were stopping once we hit 0. Well, we want to stop it once we hit the top step, right? So we're going to need to pass another value into the function to keep this going. But you'll see, I'm going to be honest, I don't know how to erase on this thing. But I'm just going to turn this into an I. if I'm just going to cross it out, okay? If I equal n, then return 1, right? Because we're going from 0 up to the third step. If we ever get to 3, we'll be like, oh, that's kind of dope. Return 1. It means we can get to the step there. And this, we wanted to stop, right? We wanted this case right here was only to stop invalid values, right? It's to say, when do we go too far? Well, when you're going bottom down, when you're going top down, you go too far once you hit the negative numbers, right? So when you want to stop at the third step, when do you go too far? When your number is greater than the number you want to stop at, right? So if, we're going to cross this out here, if I is greater than n, then we're going to return 0. It means we went too far, right? And then what we're going to do, right, since we were going top down before, we're going -1 and -2. If we're going up, bottom up, we're going to do climb of n plus 1 plus climb of n plus 2. And it's a very minor change, but what you'll notice is the results are exactly the same. So I'm going to do this one really fast, but you'll see it works the same way. Well, 0 is not in the memo, right? So we're going to say, oh, plus 1. Boom. Right? Well, we're going to say, well, 1's not in the memo, right? Okay. Well, plus 1. We're at 2. Well, 2 is not in the memo, right? Well, let's go to 3. Plus 1. Wait, we're at 3. I is equal to n. Return 1. It's a possible path to go 1, 1, 1 to get to 3, right? Remember we said once we go as far as we can go, then we're going to start doing the branches, right? So, right-hand side, plus 2. That gives us 4. 4 is greater than n, which n is 3. So 4 is greater than 3. We went too far. We're going to return 0, right? Plus 2. And we get 3 again, right? And the cool thing is you can see that both of these positive conditions are the same. If you look at this, we could reach 0 by going 1, 1, 1, 1, and we can reach 3 when we're going bottom up to go 1, 1, 1, 1. When we're going top down, we can go -1, -1, -1 to get to 0. And the paths are still the same, just the semantics are a little different. And we can see we can go 1, 2 here, we'll get 3, and we can go 1, 2 here, and we'll still get 3. Now you should be able to guess that this right-hand side is going to look the same as the other hand side. So we're going to do plus 2 here, we're going to get the 2, right? Remember in the top down, this was the first node that we could look up the value, right? That's why it abruptly stopped. Well, if you do plus 2, you get 2 here, right? And then we could look up 2 in the table, and we'll see that 2 gives us 2. So what you get is, when you're going top down, you get 2 plus 1 equals 3. When you're going bottom up, you get 1 plus 2 equals 3. So both of these are the same, bottom up. And then we're going to switch to the code, and then we're going to make the small changes that we said we were going to. Remember, like we said, just a few things are going to change, right? Since we're going bottom up, we need a number that's going to start us at 0, right? Because when we were going top down, we could just go from n all the way to 0. So we didn't have to pass anything in. We're going to pass in we're going to pass in 0, because 0 is always going to be our root node, no matter if we're looking to get to the 6th step or the 60th step, right? And we're going to keep memo. And we're going to say, if I is in memo, then return memo sub I, right? And if I, remember this case was for when we knew we had reached the value we wanted to stop. We want to stop at the top step here. So the top step is going to be n. If I is equal to n, then return n. This case was for when we went too far, right? So if I is greater than n, then return 0. We went too far. You don't get any points for going too far, right? And so memo sub I is going to be equal to, and then we're going to update this function here, I plus 1, and we're going to pass in n, I plus 2, and we're going to pass in n, and this should work the same. Return memo n. Oops, that was previous from the, and boom, this is going to be I mean, it's pretty much the same speed, basically. The only thing that might make it a little faster is due to different people running code on the servers, and that's not anything you can really do. So that is climbing stairs. And so the final thing, what is the time complexity and what is the space complexity, right? So let's take a look at the drawing one more time. So I don't have it here, but the previous drawing we said before, right? Let's just say if we have this drawing, let's just say if we start here, and if we do just straight recursion, no memoization, right? We'll be recalculating values we've already seen, right? What you get is carnage, right? Because we're recalculating values we've already seen, and then each value you have to keep calculating. And it's pretty much carnage, right? So what you get here is you get 2 to the n nodes if you were to count this without recursion, right? That's very, very, very slow. The cool thing, though, is with memoization, what you do is you reduce the solution to the problem is solved based on the depth of the tree. So once you get to the 3rd level in the tree, or the 4th, the 3rd, whatever, I don't know if this how they count levels in trees, but once you get to this level, which would be for the 3rd number, but I guess the 3rd level here, what you'll get is that you don't have to solve this again, right? And so when you solve 4, solving 4 would just be a matter of solving or just getting the value from 3, which we already solved for, and a different value, right? So this makes the solution, or I guess the time complexity, linear time, right? And so if we were going to 4, what you'd see is that you get this node, right, which would be here, and you'd probably get maybe a few more, which would be here, and maybe a few more here. What you get is this kind of really lopsided tree where what's happening is that once you solve a problem, you really never have to go too far away from your original node to get the answer. So what you get is just a really, really deep tree of n layers. And you might have a few nodes out here, right? But the thing is, you never really have to calculate. You never have to really go all the way down like you would with this version. You never really have to go all the way down. So what you get is just a really lopsided tree. It's going to go all the way down. You get pretty much n layers. So this time complexity here, because we're solving by nodes, time complexity here is going to be a linear time. And the space complexity is also going to be linear time. Well, why is that, right? Well, we're saving things in a dictionary, and all the values are going to be distinct. We're pretty much going to be saving all the values from 1 to n. You could include 0 there because if you want to, because once you get 0, if you're going top down, then you stop. Or if you want, you can include 5 or 4, whatever your stopping point is if you're going bottom up, right? And so we're storing these values in dictionary, and if you're going from 5 bottom up, you're going to have to store n values, right? And so that is 70. I don't even remember what this thing is called. That was 70 climbing stairs.